Representational State Transfer, or REST, is a distributed architectural style based on the underlying architecture of the World Wide Web. When the World Wide Web was created, there were a number of key architectural properties that were deemed necessary to achieve a robust and scalable architecture. The achievement of these properties is considered the overarching design goal of REST. These properties are performance, scalability, simplicity, modifiability, visibility, and reliability. Performance. REST aims to improve performance via the use of caches to keep data close to where it's being processed, and by keeping each interaction with services simple and self-contained. The three primary performance concerns are network performance, which includes throughput, overhead, and bandwidth; user perceived performance, which covers latency and completion time of user-based tasks; and network efficiency, which covers quantity of service interactions and quantity of data exchanged with services. Scalability refers to the ability to support a large number of instances or concurrent interactions. REST addresses four types of scalability: scaling up, or increasing the capacity of services and other network components; scaling out, or distributing load across multiple resources; smoothing out, or evening out the number of interactions over peak and non-peak periods; and finally, decoupling, or separating the consumption of finite resources, such as memory, from concurrent consumers. Simplicity. REST aims to simplify distributed service architectures in order to foster flexibility by discouraging variation. For example, the use of consistent interfaces to services and standardized media types reduces variation within a given architecture. A major contribution of REST to architectural simplicity is its usage of a uniform service contract. Modifiability is about the ease with which changes can be made within a REST architecture. This property has the following dimensions: evolvability, or the ability to change an implementation without impacting others; extensibility, or the ability to add functionality to the architecture even while services are running; customizability, which is the ability to temporarily modify services to do a special task; configurability, or the ability to permanently modify services; and finally, reusability, which is the ability to add new solutions that reuse existing parts of the architecture without modification. Visibility relates to how much information is available and can be extracted from a message without knowing any service-specific contract details. Middleware needs to be able to understand messages just enough to be able to monitor and mediate message exchanges without forming design time dependencies on specific services or their contracts. Reliability is the degree to which an architecture is susceptible to failure. Reliability can be improved by avoiding single points of failure with service implementations and connectivity. An important architectural reliability feature is the ability for service consumers to continue operating correctly over partial or total failures of their service. This requires the state of their session with the service to be persisted in a way that it's unlikely to be lost due to the failure of the service. It's also important that any interaction between a service and its consumer is supported by a feature to detect interaction failures and to recover from them. This type of feature generally relies on the ability to repeat request messages while avoiding undesirable side effects. A request message that can be safely transmitted more than once without being processed multiple times by a service is considered to be idempotent. Repeating idempotent requests is supported by ensuring service consumers supply all session state with their service requests. The properties of REST are achieved by applying a collection of constraints. These constraints are client-server, stateless, cache, layered system, code on demand, and uniform contract. The separation of clients from the server helps to establish a fundamental distributed architecture, thereby supporting the independent evolution of the server logic and its clients. From a service contract perspective, this constraint requires that a service offer one or more capabilities. The service consumer, as a client of the service, invokes a capability by sending a request message for the service to perform a task. The service subsequently replies with a response message. In this diagram, a request message is sent from the service consumer for the service to perform a task. Statelessness is one of the primary influences over service contract design in REST-style architectures. REST services are stateless between requests. A service is responsible for resource data, but must not store session state on behalf of the service consumer. This means that each request from a service consumer must be self-contained with all required session data. Any data that relates to a service consumer's session needs to be returned so that it can be stored by the service consumer. The cache constraint builds upon the client-server and stateless constraints with a requirement that response messages sent by services are implicitly or explicitly labeled as cacheable or non-cacheable. This allows response messages to be potentially stored and reused by the service consumer, resulting in partial or complete elimination of some forms of interaction over the network. Caching can increase the efficiency and scalability of consumer service interactions. It can further improve user-perceived performance by reducing the average latency during a series of interactions. Responses can be cached by the consumer to avoid having to resubmit the same requests to a service. The layered system constraint requires that a solution be comprised of multiple architectural layers where no layer can see past the next. Layers can be added, removed, modified, or reordered in response to how the solution needs to be evolved. Since the layers are independent, these changes can be made without impacting the logic of other layers. Middleware layers can be inserted transparently so that pre-existing interaction between a service and its consumer continues to occur in the same way, regardless of whether the consumer is talking to the original service or to newly added middleware. The code on demand constraint is primarily intended to allow logic within clients to be updated by the server. This is accomplished by allowing services to provide logic to consumers in response messages. This allows a service to dynamically extend a consumer with new or updated functionality. The application of the code on demand constraint typically relies on the use of web-based technologies such as web browser plugins or client-side scripting languages like JavaScript. This constraint can further be applied to services and service consumers by incorporating functionality to defer portions of logic, which is then dynamically resolved at runtime. Such an approach may be justifiable when service logic can be executed by the service consumer more efficiently or more effectively. The uniform contract constraint, also known as the uniform interface constraint, establishes a standardized parent technical interface for service interaction. It provides a consistent means of identifying resources and uniform methods to manipulate resources and standardized media types for the identification of resource types. The uniform contract further requires that messages be self-describing and that hypermedia be used as the engine of application state. The three facets of the uniform contract are illustrated here. They are HTTP methods, resource identifier syntax, and media types. This triangle of facets forms the basis of the triangle notation used to distinguish REST service contracts from non-REST service contracts. The implementation of the uniform contract relies on HTTP, the underlying protocol of the web. HTTP is widely supported and complies with the REST architectural properties and constraints. HTTP provides self-describing messages that support content negotiation and hypermedia as the engine of application state, if it's required. Let's take a moment here to do exercise 2.3. As always, we'll review the answers when you're done. Number 1. The ability of an architecture to support a large number of instances or concurrent interactions is referred to as blank. The best answer here is scalability, the ability of an architecture to grow and contract to meet capacity is scalability. Number 2. Blank is the degree to which an architecture is susceptible to failure. Reliability defines the likelihood of failure for an architecture. Number 3. A request message that can be safely transmitted more than once without being processed multiple times by a service is considered to be blank. This is the description of a service that is idempotent. Number 4. The property of blank relates to how much information is available and can be extracted from a message without knowing any service-specific contract details. The property being described here is visibility. Number 5. The ease with which changes can be made within a REST architecture is referred to as blank. The degree to which an architecture can accommodate change is modifiability. Number 6. The blank constraint is primarily intended to allow logic within clients to be updated from server-side logic to provide new or updated functionality. The code-on-demand constraint is what's being described here. Number 7. The blank constraint establishes a basic architecture that separates service and service consumer logic. This separation of service and service consumer logic is established by the client-server constraint. Number 8. The blank constraint requires that a solution be comprised of multiple architectural layers where no one layer can see past the next. It's given away a bit in the statement, but it's the layered system constraint that creates this type of abstraction. Number 9. The blank constraint can increase the efficiency and scalability of consumer service interactions and can further improve user-perceived performance by reducing the average latency during a series of interactions. The constraint that improves user-perceived performance as well as efficiency and scalability is the cache constraint. Finally, number 10. REST services are blank between requests. The correct term here is stateless. REST services should not maintain any state information. If anything, they should store state information in the messages that they return.